first introduce you to the audience. Okay. Bom dia, pessoal. Desculpa aí, teve uns 2 minutos agora de atraso, né? Mas a gente vai fazer hoje um seminário online, né? Com o professor Jong-Yong Kim. So the seminar will be in English. So I will maybe switch from English to Portuguese from time to time so that we can all understand what's going on. But let me already actually start presenting our guest in English then. So Professor Jong-Yong Kim, he did his bachelor at Korea University and his PhD at the University of Cincinnati in the States. And he was a postdoc at the University of Illinois at Urbana-Champaign. By the way, Jean-Lex from our department, he was also at that university, but you were there in 1998 to 2000, right?
Right.
He was there, I think it was already 2003. He was working with Jean-Pierre Le Bourton. Did you meet this professor there, Jean-Pierre Le Bourton?
Doesn't.
No?
Yeah, I don't recognize right now,
yes,
but
he is Jean-Pierre Le Bourton. He was in the electrical engineering department, I think. I'm not sure if Jean-Lex is in the audience here. Maybe he can talk to you about that too. So he was senior researcher at the ETRI, then professor at the Incheon National University in Korea, and visiting scholar at the Wake Forest University. And he's currently professor at the department of what's the name of the department? Sorry?
Energy science.
Sorry,
Energy science.
Yes, energy science. Sorry about that. Yes, the department of yes, it's in the slide here. I'm sorry about that. I was reading your information in another. Yeah, so he's in the Department of Energy Science at the Sungkyukwon University in Suwon, in Korea. So thank you very much already for having the time to talk to us about your research. So you can already start your seminar.
Okay. Thank you, Andre. It's a great pleasure, actually. To give this presentation. So I don't see any audience in my side, so I don't know whether.
Yes, indeed. Actually, that's a problem with the system that we use. If you want to see the audience, they are actually in the YouTube channel. So then they are like watching us live on YouTube, and they give some comments. And I see their comments here in a slab, like by the side of the software that we are using, of this platform that we are using. Do you see something on the right where you can see the no, right? So then it's just the host that can see this here. Otherwise, if you want to see something, then you need to be in the YouTube channel of our department.
Can you quickly send me the link?
Yes, I can. Yeah. Okay. So let me.
At least I can. I don't feel that I'm talking to.
Yeah. Because right now you see there are 17 people there. So.
Okay. Great.
Let me send you the. But anyway, when they ask questions, I will click at some button here, and then the question will appear in the screen, and then you see the question there.
Sure. Okay. Yeah. Well, I mean, I gotta say that I prepared this presentation in a very casual manner. So.
Yeah, no problem. That's fine.
Yeah, I just I don't know how much you would be interested in this specific topic, and so I'll just give what I've been doing for the for the last few years, and I mean, just I wanted to share things that I found interesting, at least for myself. So hopefully that also gives some point that you may find it interesting. So So I'll just start then, I guess. Okay, yeah. So okay, well, let me
So
see.
just by the way, I just sent you by email the link for the YouTube channel, and then you can see there if you
Oh
want.
yeah. I see that. You know what? I'm just gonna open this quickly.
Yeah,
Oh yeah. There you go. Okay.
yeah.
Uh,
So by the way, what they are writing there, "Bom dia" means good morning. So that's. And
okay.
you've been to
So
Brazil, boss. Maybe you've been to Brazil, right? Or
yeah. I've been to a
to
couple of
Maceió,
times.
right?
Right. Actually, last year, the Brazilian MRS. So.
Yes, yes.
So, oh yeah, I see. A lot of people already came in. So, thank you very much.
Yeah.
I'm sure now that I'm not alone. so,
Yeah.
I feel much better. So, I think I can comfortably start now. Okay. Okay. So thank you very much. So title is over here, and this is basically regarding to van der Waals layers semiconductor, or we call two-dimensional semiconductor, and we are interested in tuning and manipulating this exciton behavior, and hopefully we can use those for some application of quantum optical devices. So let's see. Let me start. Okay, so I want to start with thanking my group. Actually, I have a few more, but I listed the members who contributed majorly the topics that I'm going to present today. Krishna and Unji and Trang and Anil. And of course, I have a lot of collaborators, and Andre is over here, Yara and Ingrid, and they are just wonderful. So I had Andre last year in our department. He gave a wonderful presentation, and we just enjoyed this so much. So I thank the our research foundation, of course, for the support to make it this possible. Okay, so actually I have two topics today. The very recent result actually. So one is we try to intercalate this multilayer MoS₂, and then we try to have this actually acting like many monolayers. And then another recent result is regarding this new type of TMD called the rhenium disulfide. And then if you have those in stack, and then this twist angle can give you very interesting measure to manipulate the excitonic features. So I'd like to discuss that too. Okay. Well, before let me see the watch so that I don't over time. Okay. So I guess you are already very familiar with the what is the semiconductor, but I just prepared a couple of slides just to just the fundamental things relevant to our research. So basically, semiconductor comes with the bandgap, and this bandgap is the the source that can give all various this color of emission in this semiconductor. If you take one example using a semiconductor, and that's because this recombination of electron hole across the conduction band minimum and valence band maximum. So this energy gap is of course very important. But the another thing that we have to consider is actually momentum. For example, the silicon is of course the the most popular semiconductor in semiconductor industry, but they don't have this matching of momentum for the photon to deal with. So that's why the silicon is not really active for light application. So this type of semiconductor is called the indirect bandgap semiconductor, while this where these two minimum minimum and maximum has the same momentum value in the band structure. They are called the direct bandgap semiconductor. So of course, in terms of light emitting application, being direct bandgap is a huge impact, giving a lot of benefits over indirect bandgap semiconductor. So when another the concept that I'd like to just remind you is actually exciton. So I already discussed the this bandgap, and then finding out what the bandgap energy is. Of course, if you run the UV visible absorption spectroscopy, and then you see this clear absorption edge. Okay, that of course corresponds to energy of a bandgap. But if you run this absorption measurement in a very low temperature, and then you see this, the very strong peak that you don't see in the room temperature measurement, and that's actually the evidence of this exciton formation, because you have a electron hole due to the light absorption. And of course, they charged with the negative sign and the hole with the positive sign. So these two particles will form the this Coulomb binding. Okay, and this acts like some kind of a quasi particle, and comes with the binding energy. Okay, which is very small for a 3D semiconductor like a gallium arsenide. Their binding energy is like only 4.5 MeV, and this is much smaller than the thermal energy for a particle, any particle in temperature. So room temperature thermal energy is around 25 MeV. So you don't see this formation of exciton in room temperature. So you have to bring the sample down to very cold energy, a cold temperature, to see the formation of this exciton. Okay, but this two-dimensional TMD material that we call two-dimensional semiconductor, or van der Waals layered semiconductor, is actually comes with the very interesting features. I mean, I don't want to spend I don't want to discuss all those interesting features here, but I just want to point out that for example, this MoS₂ is normally indirect bandgap semiconductor. Okay, but if you isolate just a single layer, okay, because you see it's a van der Waals interaction material, so you can peel out a single layer just like you would prepare graphene, and then they become a direct bandgap semiconductor. Okay, so that's of course the point that we find very appealing. Okay, and another fascinating thing about this TMD material is you have a numerous combination between this transition metal and then chalcogen atoms. Of course, the MoS₂ was one of the first materials, this two-dimensional semiconductor that has been discovered, but later on you have like all kinds of combination, and especially today I'll discuss the MoS₂ and then rhenium disulfide. Okay. Okay. So here goes. Okay. So okay. So to prepare this monolayer TMD, as I discussed, if you prepare in the form of a monolayer for with this TMD material, and then you will get this direct bandgap semiconductor, okay, which is very nice, okay. But if you have just a monolayer, okay, I mean there's a challenging point like. Of course, you can use this Scotch-Tape method, which is of course, the standard method. But this is very accidental process. Okay, yeah. So you don't get like a large size. So this is something. This is not something you can use it in practical application. Okay, of course, people now can prepare using CVD. To obtain a very large area monolayer TMD, but also, I mean, that's kind of challenging task, and the crystal quality of the CVD grown TMD monolayer is not as good as the monolayer TMD you will get using this mechanical exfoliation. Another limitation would be, of course, it's a monolayer thickness. Okay, it's a slightly larger than the graphene thickness, but still it's less than 1 nanometer. So it's very fragile. Okay, and of course the light matter interaction that you can expect is also quite limited. Okay, so idea is, I mean, is it possible that we could have like a multi-layer TMD? Okay, something you can get very incidentally and without much effort. Okay, but can we make it to have monolayer characteristic? Okay, so that was the kind of motivation that we had for this project. Okay, so previously. Okay. So in some time ago, we are kind of studying that what would happen if you inject very high density of electrons into this multilayer MoS₂. Okay, and there we used this so-called the solid electride that comes with a very low work function, and then you can actually inject the very high density of electron into MoS₂, and then you see very strong doping effect and the narrowing of a band gap and so on, and then finally you can actually turn this MoS₂ into metallic phase. Okay, so MoS₂ actually can be metallic and semiconducting. So that was our kind of previous project, and one thing that we found out in this project is there's a very heavy modification of a band structure. Okay, and then there's some hint that this may act like the direct bandgap semiconductor. Okay, so that's why we saw after the electron doping, we observed a very strong enhancement of PL. Okay, so multilayer MoS₂ is being indirect bandgap semiconductor. So you wouldn't expect the strong photoluminescence. Okay, but it was displaying very strong photoluminescence after the electron injection. So there's some hint that the interlayer interaction between the layers in MoS₂ may have been weakened because of very high injection of electrons. So, the interlayer distance may have been widened. Okay, so there was some indication of that. So we decide to kind of go further on that direction, but this time we used kind of organic chemical, and what this can do is actually they can kind of get into the gap between the layers. Okay, and then also another effect that this intercalation provide is actually the high electron doping as well. Okay, so I'm not gonna go through too much detail about the electrochemical intercalation process, but what it does is basically this EMIM plus molecule getting between the layers, and also some electron injection. Okay, yeah, this is kind of the photo of the sample, and this is the scheme of our sample. Okay, so if that actually happens, then we can expect that it used to be multilayer MoS₂. Now we can expect because they are far enough between the layers, and then they each layer may act like monolayers. Okay, and then one thing that you can expect is, of course, the very strong photoluminescence, because now this used to be indirect bandgap semiconductor, okay, because it's a multi-layer, but now it's like multi-stack of monolayer MoS₂. Okay, so we took the PL spectrum. Okay, actually same sample. Okay, so this black curve is the PL from pristine sample. Okay, so we have actually two peaks, one over here and the other over here, and this is the direct band gap transition, and this is the indirect band transition. And as you can see, indirect band is less energy, so that's what makes this to be an indirect band gap semiconductor. And also the intensity of a photoluminescence is almost 10 times higher than direct band gap transition, okay, which is the typical feature of an indirect band gap material, indirect band gap semiconductor. And now if you do this EMIM intercalation, and then what happened is we still have those two peaks, okay? Direct band gap peak over here, and then indirect band gap over here. I mean, they have shifted their position, okay, and with the proper region, of course, okay. But this is the indirect band transition, and this is the direct band transition. Okay, so overall intensity is actually about 70 times. Okay, so before intercalation and after the intercalation, we are talking about the same sample. Okay, and now we are getting, with the same condition of excitation and everything, we are getting almost 100 times, 2 orders of magnitude increase in PL. And I have this as a comparison. Okay, the monolayer photoluminescence, and actually this becoming even stronger than monolayer, the MoS₂. And furthermore, if you quantify the ratio between this indirect band gap and direct band gap intensity ratio, it used to be about 9 times. Okay, so this is like 1 order of magnitude stronger in intensity. again, which is the signature of indirect bandgap semiconductor. And now it, their ratio reduced about 2 orders magnitude. Okay, so that's why we call this as a bandgap crossover from indirect to direct bandgap semiconductor. Okay, if you do this same experiment in the yeah, so actually this whole enhancement duration and everything changes with the laser power. Okay, so if you reduce the laser power, and then you start having difficulty in getting the luminescence, photoluminescence from the pristine sample. Okay, but in terms of enhancement, is actually even larger. If you do the same PL experiment in the low temperature of 3K, and then of course the it's low temperature, so indirect bandgap transition now is much weaker, because that requires the phonon participation. But I mean, general trend like increase of a PL and the this decrease of ratio between indirect and direct bandgap is exactly the same. Okay. There's another interesting that we can notice is there is a very strong end-doping with this intercalation process. Okay, there is a in these 2D materials, 2D semiconductor, you have not only exciton, also you have this charged exciton that we call trion. Okay, and the spectral ratio between this exciton, neutral exciton that we call, and the trion is used to be, the trion portion used to be very small, okay, for pristine sample, but after the intercalation, on top of this huge enhancement of PL, there is a very large increase of trion portion. Okay, that means the this sample now is very electron rich. If you run the Raman measurement, and then there's a peak that's kind of a specific to the either strain or electron density, and then the Raman spectrum also indicates there's a very strong electron doping with the this intercalation process. Okay, and the yeah, that's something I think I'm just gonna skip. Oh, and also if we've been talking about intercalation, making the gap distance wider, okay, and then of course there should be overall increase in thickness of the sample. Okay, that's something we commonly observe. Okay, so from the pristine to after the intercalation, we have about the 50% of thickness increase throughout the sample that we inspected. And of course, if you look the cross-sectional STM, and then that also shows the the features. Okay, is that the all that you can expect from intercalated sample? Well, there is another advantage or application that you can expect from monolayer TMD. Is actually the phenomena that people call the valley polarization. Okay, again, I mean, I don't want to spend too much time about what is this valley polarization, but let me just simply describe as there are in the band structure of MoS₂, you have this actually two momentum, the valley in momentum space, okay, that we call K and K prime, and they have the same transition energy. Okay, so they degenerate in terms of transition energy. Okay, but actually you can separately populate these two values, okay, using the circular polarization. If you use the normal linear polarization, you will populate this valley with the same population, same probability. So you wouldn't be able to tell the presence of this degenerate the valley. But if you use the circular polarization, either left or right, and then you can actually separately excite, and also you can detect the emission from separate valleys. That's what's called the valley polarization. And this is kind of typical result that you can expect from MoS₂, okay? But you have to do this only in low temperature, because in high temperature, there is so-called the intervalley scattering, very active in high temperature. So you don't see this separate addressing of these two valleys. Okay, so you don't see this valley polarization anymore. So this is something very interesting in terms of a quantum quantum optics. Of course, this was discovered a long time ago. That the so if you do the valley polarization for monolayer MoS₂, pristine MoS₂, and 70% of degree of valley polarization is something you expect. Okay, so now we claim that you can convert this multilayer MoS₂ into stack of a monolayer MoS₂, and then this valley polarization that you don't see from multilayer MoS₂ should appear. Okay, so that's exactly what we observed. We observed about 55% of valley polarization from multilayer sample. Okay, and interestingly, we observed about 16% even in room temperature. This is something you don't see even from monolayer MoS₂. Okay, and this is the plot of degree of polarization as a function of energy, and this gray curve is the degree of polarization for monolayer MoS₂, and as you can see, this intercalated sample is actually comparable to the degree of valley polarization that you expect from monolayers, pristine MoS₂. So this is really demonstrating the desirable or useful characteristic of a monolayer by using the intercalation of multilayer MoS₂. Okay. This valley polarization is something that we commonly observe from all various sample. Okay, so it's not something that we obtain from specific sample. I mean, this is general observation that regardless of the thickness of the sample, either in low temperature or room temperature. Okay, so there's a reason that we see this room temperature valley polarization is because this this intercalated MoS₂ has the high density of electron, and this trion is tends to display stronger valley polarization than neutral exciton. Okay, so that's why we are seeing this room temperature valley polarization from our intercalated monolayer multilayer MoS₂. So that's it. Yeah. Okay. So okay, and then let me move to second topic. Okay, and this is another way to control the interlayer interaction. Okay, so previously we used the intercalation to adjust the interlayer distance or interlayer interaction. Okay, but here what we did is using this twist angle between this homo bilayers of rhenium disulfide. Okay. Okay, so this rhenium disulfide, we actually, for the last few years, we kind of, did some work, and also we tried to, do the heavy doping of electron. In this case, we use the lithium intercalation. Okay, and then interestingly, in pristine stage, this rhenium disulfide is actually it's a anisotropic lattice. So electrical curve or the optical response is anisotropic. Okay, but we found out the if you do the heavy electron doping, and then this degree of anisotropy is actually can be removed. Okay, so actually this twist of this bilayer, people already studied this phenomena a lot, and people already found out this twist angle is a measure of tuning the interaction between the layers. Okay, so if you look at the Raman spectrum, that can probe the interaction strength between the layers, and then they all show the specific the tendency, and commonly what was happening is within this very small angle, of course, there is some change of interlayer interaction, whether it's completely aligned or misaligned. Okay, but the trend is this type of change occurs within a very small angle. So every change occurs in very small angle. Okay, so that's something people found out with the this MoS₂, which is the isotropic lattice. Okay, but rhenium disulfide is anisotropic lattice. So we are wondering what would happen, if we do the twist structure using this anisotropic lattice of rhenium disulfide. Okay. Oh yeah. So using this for this bilayer MoS₂, we did some similar work very long time ago now, 10 years ago, and then we also observed this change of interlayer interaction. Actually, this one is actually monitoring the peak position of indirect peak, because now it's a bilayer MoS₂. So you see this interlayer, I'm sorry, not interlayer, indirect band transition. Okay, and then it would have this very clear dependence with the twist angle. Okay, but over here as well, all the change occurs within the very small angle. Okay. Okay, yeah, and the our work and the some other works too. Okay, so these are the sample structure that we prepared. Okay, so basically we have two rhenium disulfide on top and at bottom, and we made the various angles of stacking. Okay, Okay, so here is the result on photo limit. So monolayer PL is something like this. Okay, it has a characteristic 2 peak. Okay, and then if you make it bilayer, okay, so this is intrinsic bilayer, and then you have this 2 peak, and then there is another peak coming newly. Okay. But if you just look at the X1 and X2 peak, and then you see there's some shift between monolayer and bilayer, okay? And interestingly, if you take the PL spectrum and the the estimate the peak position for X1 and X2, and then at 0 degree or 0 degree means the intrinsic bilayer, of course. There is no angle. Okay, so theta is 0, and now we use the 2 monolayers, and then we make the all different angle of twist, and then interestingly, okay, within this window of a peak position of a monolayer and bilayer, okay, and then it starts from the bilayer value, and then slowly increase, and then it quite approaches the value of a monolayer. So we are kind of very excited. I mean, is it indicating that it starts from the bilayer, okay, and now if you twist it, and then it starts to losing the interaction between the layer, and then if it becomes more than 10 or 15 degree, and then it resembles the PL properties of a monolayer. Not, quite the same as the monolayer peak, but it's approaching very closely. Of course, the Raman spectroscopy is more powerful technique to probe the interlayer interaction. So we had this colleague who is very good at analyzing this interlayer interaction, and he can, even estimate what kind of interaction strength between the layer is based on the this layer breathing Raman mode. Okay, and as you can see, the interlayer interaction is actually start from over here and then quickly reduced, okay, within 10 degree, and then kind of saturate. So we are getting this almost 30% of a reduction of interlayer interaction just by the twist angle. This is something we don't see from isotropic TMD. Okay, of course, we see this dependence of Raman, this layer breathing mode, and indirect peak position, but this direct peak position doesn't change at all. Okay, so there is a slight variation of interlayer interaction, but not as much as the that we see over here. Okay, this is a huge change to 30% of interlayer interaction just by the twist angle. This is something very specific to this anisotropic lattice of RES2. Okay, so this is low frequency Raman spectroscopy, and this is conventional high frequency Raman spectroscopy that shows the age-like and EG-like, but their overall trend is consistent with the this layer breathing mode dependency. Okay, and we also had a collaboration with the Sean and Martin at Montana State University, and they ran this DFT calculation to look at the how the band structure changes. And interestingly, we start to see this flat band characteristic at the low angle twist. Okay, and this flat band is quite, the bandwidth is getting very small with the right. Yeah. So okay. Yeah. So this is okay. Yeah. So this okay. So this is a Moire super lattice period, of course. But this is the angle of a twist. So as you can see, angle of a twist, less than 10 degree, and then the flat band characteristic appears. Okay. And of course, I mean, the thing that we were more interested in, just for our work is, of course, this band gap increase with the twist angle. So this is consistent with our observation too. Okay. Okay. So the conclusion is we formed the twist bilayer random disulfide. Okay, and then by controlling the twist angle between 0 and 10 degree. Exciton energy was tuned to over 40 MeV. This is, almost the full range between the exciton energy of pristine monolayer and bilayer radium sulfide, disulfide. This is a very large value that you cannot really expect from isotropic, the TMD. Okay, so yeah, that's it. Like I said, I prepared the two project, recent two project that we've been doing. So I think that's all I have for today.
Okay. So thank you very much. So let's give him some applauses, although you cannot hear anything because it's just online, right? Yeah. So
That's
now
fine.
but thank you very much again for the presentation, for taking the time to talk to us about it. And now I will open this session for questions, and then students can ask questions in the chat here, and then I will click on the questions and they will appear in your screen too, in your screen here in the StreamYard platform. But I can also read the questions. Se quiserem perguntar também em português, eu posso traduzir, viu? So if they ask in Portuguese, I can also translate and see how it goes. But let me already start with some questions myself too.
Okay, yeah, sure, yeah.
Yeah. So actually, just already about this last topic that you talked about, this interlayer coupling in granular disulfide. This is nice because I remember there was a paper from our collaborators in Belgium, in Antwerp. So it was actually a big collaboration there. It was people in Belgium and also Sefati in Tongai, I think in the States, and some DFT people calculating stuff from a department in Turkey. And they were discussing the fact that in granular disulfide, it's especially hard to get interlayer coupling actually. So they say that if you go from one layer to more layers, because you did only one layer and two layers, right? If you go from two on, it seems that there is not so much of a difference in the end. I think this paper is published. I found it here, the reference. Let me see. It's a Nature Communications. I can send you the reference later on. So this means that what they were claiming is that granular disulfide is already different from the rest because of the interlayer coupling, in terms of interlayer coupling. So then in the way that you are doing, you are using wanting to tune this interlayer coupling. I think it's very useful for the community, I think. Yeah.
Okay. Yeah. So yeah, I mean, rhenium disulfide is a very interesting material, and people even say it kind of maintain direct bandgap characteristic. even with the multi-layers. So that's also kind of indication that the interlayer interaction itself is not really as strong as the isotropic TMD. So I think that's kind of the key, that we are seeing this very large room of tunability, because their interaction is kind of a subtle. So this twist can make, such a lot of, such a big difference.
Yeah.
So, and also, I mean, because the lattice is anisotropic, so we are talking about much larger degree of freedom here.
Yes.
So they have a like a main axis that we call B axis. Okay, so we start from there. So they have a main axis to begin with. So when you make a twist from there, you expect a much stronger effect.
Yeah. By the way, you showed some kind of dichroism, like this anisotropy in the photoluminescence when you make this polar plot. And when you show that it becomes not, it loses the dichroism if you put lithium or something, right? Or
Yeah. This is our work. Yeah, previous work. Yeah.
yes,
So,
but then if you rotate, do you also see something different when in terms of this of the anisotropy in the polar plot?
oh yeah, that's a good point. Actually, I didn't include that part. We in this publication we also have the TEM study with the all different angles. So and also we perform the this polarization as well. So of course one thing, this anisotropy, the very clear anisotropy is heavily modified
Yes, that's what I
if,
was.
if you have this twisting. And the thing is, but yeah, it's very well, what do you say? It's very complicated actually to simplify. But of course, there's a very large modification of anisotropy if you do the stacking. Yeah.
Yeah, and still in this thing with the of the dichroism, I see that also in the first part of your presentation, you showed some result of MoS₂ intercalated and so on, where first it was circular and then you found something like with this anisotropy too, right?
Yeah. That also our previous
It
work.
was surprising for me. So
Well,
that I
yeah.
have a direct question about it. Let's see. Yeah, this one. Yes. So
Yeah.
what? How does it inherit this thing? Where does it get it from?
Well, I mean, so this is like a kind of opposite side, because MoS₂, so the 2H type MoS₂ is isotropy lattice, being semiconductor. Okay, and
Yeah.
now
Ah,
it can
okay.
become a
Became
metallic.
empty. That's why. Okay, that's why.
Yeah.
Yeah.
So,
Yeah.
but the RES2 start from being anisotropic, still being semiconducting.
Yeah.
So it's so with the electron doping it can be isotropic, but over here MoS₂, used to be isotropic, but by becoming metallic 1T prime, the distorted lattice, and then we start to seeing this anisotropy.
Okay. Oh, that's fine. Yeah. Okay. Yeah. I got it then. Yeah. And also, I see that you have a very practical point of view. I remember when we collaborated, it was also about making the enhancing the power of emission in light into the materials, like by trying to avoid these exciton-western annihilation and things like that. So A few days ago, I was talking to somebody about these things with the applications, future applications of 2D materials. And this was a guy who was really like into making devices, but usually for transport. And he was saying like, yes, but there is a problem that if you try to make devices with 2D materials, it's possible that they may slide on top of each other because of the van der Waals interaction, that it's weaker. So then I got curious, like I just remembered to ask you if does that happen somehow? Sometimes do the samples slide? Because I'm a theoretician, so I'm not really familiar with problems with experiments.
Yeah. Yeah, I'm not that much familiar with that. But what at least it's not just as simple as the the rigid lattice twist. It's actually yeah. I mean, they kind of commensurate to each other when you have this stacking, and with a different twist, of course. And I understand that even and the thing is, either of those configuration, either sliding, whatever you call, one of them, happen to be more stable than
Yes,
others.
yes.
So
at some point they will stabilize somehow, right? Yeah.
I'm sorry.
At some point they will stabilize. They will become stable at some configuration, then, right?
Right. But for our purpose is so when you have a certain angle, it's just, I guess, a unique configuration. I don't think there'll be like the multiple configuration with a certain angle. I think you give a certain angle, and then it just somehow stabilize into certain configuration.
Yeah. Okay. So one of the students asked it here. But she asked it in English, in Portuguese. Then I can translate to her later on if you want. But she's asking like if you can explain how are these polar plots that you have there. She doesn't know the meaning of these plots.
Oh yeah.
So yeah.
Oh yeah, I'm sorry. I kind of just went over. Yeah. So this polar plot means the intensity of a Raman peak. So intensity starts from the zero to certain normalized value on the parameter. Okay. So it's just the representing the intensity at each angle of a polarization.
And
So
that's for a Raman, right? For Raman peaks, right?
right. So this is the actual data, and then this is the result that you can plot in polar polar plot. Okay.
Yeah.
So
And the angle is the angle of polarization of light that you use for the measurement, right? Or
right.
so let me explain to her like because this is actually it's common in our field, but it can be not common to some other
Oh
fields.
yeah,
That,
of
yeah,
course,
yeah.
of course, of course.
Viu? Então, só para explicar então em português também, esse é um gráfico que, assim, nessa área de materiais 2D, as pessoas têm feito muito isso para ver se o material tem uma direção preferencial para fazer coisas, sabe? Para, tipo, emitir luz, por exemplo. Esse é um experimento de Raman, feito com a luz polarizada num ângulo, que é esse ângulo que está no círculo aí, que vai de 0 a 360, né? E aí, os pontos, quanto maior for o raio, mais intenso é o pico que saiu daquele ângulo, entendeu? Então, por exemplo, o que é que acontece com esse 2HMOS2? É simplesmente o MOS2 comum, ele não tem nenhum tipo de anisotropia. Você vai botando ângulos completamente diferentes, a intensidade do pico Raman é sempre o mesmo. Agora, se você pegar MoS₂ dopado com esses elétrons e tal, aí ele vai para essa fase 1T, essa fase é anisotrópica. Se você botar 0 graus ou 180 graus, a intensidade é bem grande. Mas se você botar 90 ou 270, a intensidade é bem baixinha, por isso o raio fica bem pequenininho e fica 0 lá. Né? Então a intensidade é baixa, ela só é alta se ela estiver polarizada numa direção, a intensidade desse pico Raman. Aí você consegue entender qual é a fase que ele tem por causa disso. Né? So that's the explanation, and in Portuguese now too.
Okay, thank you.
If students have more questions, I will give them 1 minute to write something about it, to write some question here in the chat. Otherwise, in 1 minute, I will just finish the session.
Yeah, I mean, even after afterwards, I mean, if you just forward the question, then I'm happy to answer the question. Okay, later.
Yeah. Okay, I can forward you any questions that they
Sure.
make. Yeah. But it was a very nice talk actually. This idea we discussed already, this thing with the intercalation of MoS₂. I think this is a very nice way to solve the problem of it's not even like stability of the system itself, but the stability of how to produce it, because exfoliation is really bad. It's every time you get I mean, I know that people will say that exfoliation is nice because every time you get a nice sample, but there will also be high quality. It's a high quality sample. But on the other hand, it will be a different sample every time you get. So that's
yeah. So I mean, for both projects, actually, we are going further. So I'm still working on this intercalation to have even superior property, and also for this anisotropic lattice twist as well. And so I briefly mentioned this appearance of flat band, and of course those flat band is kind of suggesting a lot of interesting phenomena.
Yes.
So yeah. I mean, I'm still our guys are working on this this project for more. So I may have something that I wanna discuss with you later too.
Okay. So thank you very much again, and thank also for the audience to come and watch our session today. So thank you very much, and have a good night there.
Okay.
Thank you, pessoal que está aqui.
Oh yeah, thank you for this opportunity, and I also enjoyed it. Yeah, it's kind of a new experience for me. So is this a YouTube?
Yes, it's on YouTube, and then it will stay.
So I can. It will be there later too. I can watch myself too, I guess.
Yes, you can. Yes, it will be later. Okay. It's going to be recorded there in the site and in the website, and then it's in the YouTube channel.
Okay. Wow.
Yeah.
That's great.
You can see also there are also some previous seminars like that there too. If you are interested.
Okay.
You can watch there.
Yeah, I'll kind of look through it to find anything interesting for me. Okay.
Okay. So thank you very much.
Okay. Thank you, Andre. Talk to you later. Okay. Take care.
Later then. Bye.
Bye.